build AI systems that are as good as humans. And of course, AI is in the conversation. I mean, it's a household word today. Everyone talks about it. So I'll give a little bit of history of AI, essentially a little bit of background, a little bit of history of AI, and then kind of look at the current state of the art, and then see how we can actually achieve this artificial general intelligence, or AGI as it is known commonly. So I want to acknowledge the support from many funding agencies and many companies that have gone into doing some of my research, and also, of course, my PhD students who contributed a lot. So let's start by talking about artificial intelligence. Intelligent reasoning by computers has been a goal of computer scientists ever since computers were first invented in the 1950s. And so the question that you want to ask, so computers were invented right around what first machine was built around 1957, 58, around that time framework. And since then, people have been interested in, and actually the first uh, program that was developed that could be called AI was the program to play the game of checkers. So the question you want to ask is, what is intelligence? How do you define intelligence? And so I would say that intelligence has two broad components. One is our ability, or human intelligence in this case, our ability to learn. And so we learn by observing, and then of course, people may teach us as well, right? We acquire knowledge by, from others. And we also learn by observation. And then we also learn to recognize things. And essentially in learning, we use pattern matching. If we automate the learning process, then that's what is called machine learning. And then once we have this knowledge, once we learn this knowledge, we actually apply it. So, for example, I might learn the pattern as a kid. If I drop a mug on the floor and it shatters, it's a ceramic mug. And then after maybe two or three times, I might realize that, I should not drop certain objects. So what has happened is that I have essentially learned a rule, learned this knowledge that certain types of objects, if dropped, will break. And this rule now resides in my mind. And then subsequently, if I encounter such an object and I'm holding it, then I'll apply this rule to essentially know or conclude that I should hold on to this object more tightly. So this process of applying knowledge is essentially reasoning. So learning and reasoning are two broad components of intelligent behavior, you could say. And if we, automate these two aspects to obtain, what's called machine learning and automated reasoning, and that's basically, essentially what artificial intelligence is. Of course, there's also things like vision, speech processing, speech generation, etc., that we see in us humans. But the underlying two methods that you could say constitute intelligence, two things that constitute intelligence are learning and reasoning. So of course AI has been receiving a lot of attention lately, and then when you hear the term AI, the question is, what does it mean? And in today's context, actually, when people say AI, they really mean machine learning or deep learning. And in fact, it did not used to be that way. So this has sort of happened in the last 10, 12 years. But, going back into the history of AI, if you mentioned the word AI maybe 20, 30 years ago, then people would assume it to mean automated reasoning rather than machine learning. Of course, the history of research on machine learning as well as automated reasoning is old, and and actual research in AI, both aspects, both the reasoning aspect and the learning aspect, started in the 50s or even before, you could say. So the next thing we want to ask is, how does machine learning work? And I think most of you already are familiar with the concept of machine learning. So machine learning essentially involves that you have some background knowledge, and you have positive and negative examples of a concept, what is called training data. And then the goal is to learn a general rule or a function that captures that concept, what's called a model. And once you have the model, then that associates, you know, uh, these examples with a classification, then you can use it for prediction. So for example, I have examples of pictures of birds and pictures of non-birds that could or could not fly. For example, planes can fly, but I might have other non-examples of birds, such as, chair or a table or something. And my goal is to be able to recognize um, what a bird is. And and learn that concept automatically, so that if I'm shown a picture, once I learn the model, if I'm shown a picture of the bird, I should be able to recognize that, yes, it's a bird. And if I'm shown a picture of say, a table, then I should be able to say, no, it's not a bird. And there's a lot of research that has gone into machine learning, include supervised learning, unsupervised learning, reinforcement learning, transfer learning, all sorts of things. So the next question thing I want to explain a little bit is what is automated reasoning. So, or formally defined, or maybe informally defined. So automated reasoning can be thought of as that you're given pieces of information, or what are called axioms. We want to deduce new knowledge or draw new conclusions from these axioms. So, for example, think back high school geometry, where you learned Euclid's axioms, the five axioms of Euclid in geometry. And then I'm sure you remember doing a lot of proofs, for example, proving Pythagoras' theorem, where you take the knowledge that is expressed in these axioms, you combine this knowledge to eventually show that you can derive the statement of Pythagoras' theorem. So, for example, I have two statements: that all humans are mortal, and that Socrates is a human. Then I can conclude that, right, since Socrates is a human and all humans are mortal, I can conclude that Socrates is mortal. So machine learning has a long history. Techniques such as Bayesian network, Markov chains, least squares, probability theory, perceptrons, and neural networks, all these things have concepts have played important role in development of machine learning. And these techniques have a history that goes back far. So you may or may not know, for example, that Bayes' theorem was discovered in 1763. So that's almost, more than 250 years ago. And the idea of a perceptron that led to neural network is from the 1950s. And algorithms, techniques like backpropagation that play an important role, today in neural networks, date back to the 70s and 80s. In 1983 was the first international conference on machine learning uh, that was organized. So many people think that machine learning is a very recent technology. It is not. It's been around for a long time. So today we have neural networks, deep learning, large language models, of course, and many innovative applications of machine learning become possible because of the web and internet. We're collecting huge amount of data. And then, of course, we have computing power in the form of NVIDIA, and now NVIDIA GPUs, and now we can take this huge amount of data, and of course we have these very impressive fast machine learning algorithms, and so we can put these three things together, and now we can essentially ask questions to data, and you could say that every field has big questions it wants to answer, and these answers essentially are sort of hidden in the data. So that's what machine learning is about. So automated reasoning also has a long history. Logic and inference procedures play an important role in automated reasoning, and the history of logic, of course, is very old. So it goes back to Aristotle, who wanted to formalize the thought processes through this notion of syllogisms. And in fact, in India, it goes back even further, where this concept of Nyaya, so it's one of the six shastras is Nyaya Shastra, going back to 6th century BCE. And it's actually quite interesting that if you look up some of this work on logic in ancient India, it's quite impressive, the kind of things that were discussed back then. So modern logic begins with George Boole in the 1850s, wrote this book called Laws of Thought in 1857 or 1856. And that's where Boolean logic, that most of you would be familiar with, or propositional logic, came about. And then in the around 1879, Gottlob Frege defined predicate logic or set theory. And all this was motivated by this enterprise in mathematics to automate the proving of theorems. And then, of course, in 1930s, Herbrand actually came up with an automated theorem proving procedure. And in the 60s, so if you actually read, study automated theorem proving and Herbrand's theorem proving procedure, you can actually see how Robinson, who invented the resolution principle that formed, much of the basis of reasoning in AI since the 60s, you can actually see, how Robinson could have discovered that how you could make Herbrand's procedure more efficient, and that leads you to the resolution principle. And today, of course, we have advanced theorem proving systems like, Otter and Lean and Coq and, very practical ones. And then you have advanced logic programming languages such as Prolog. And we'll talk a little bit more about logic programming languages, as we talk about artificial, general intelligence. And then you have advanced rule-based systems. And then, of course, foundation of much of traditional computing traditionally has been in logic. So now, of course, logic, I mean, AI has been around for a while. There have been many successes. So let's talk a little bit about, successes of AI or publicly known successes of AI. So all of you, I mean, those of you old enough, or if you're not old enough, you might have read about this Deep Blue system, that chess playing system that beat Gary Kasparov, and this was purely based on automated reasoning. And then, of course, you may remember Watson that won this, game of Jeopardy. That's a popular game show in in US. And actually, Jeopardy used both machine learning and automated reasoning. So machine learning actually was a critical component in making sure that. And so what they did was they took all the questions that had been asked in the show for the last whatever 50 years, and then trained a model to essentially figure out what part of the question should focus on to get the answer. And that actually worked really well for them. And in fact, the Watson system was actually able to beat the top two champions of Jeopardy over a 2-day competition. And today, of course, you have systems like AlphaGo. So people thought that the game of Go, but computers could not beat a human in the game of Go. But then AlphaGo system, again, this is like 2016 or so, using machine learning alone, researchers were at this company called DeepMind were able to design a system that actually could beat the world champion. And of course, you have these self-driving cars that rely uh, on machine learning. And of course, today we have generative AI and large language models that we'll talk a little bit about. Of course, machine learning has been enormously successful, and it's a great technology because all you have to do is to collect data, feed the data to a machine learning system, and then out comes this sort of learned function that maps input features to labels or to outputs. And then once you have learned this function, now you can apply it everywhere for prediction. So it's an wonderful technology and very easy to use. However, it has many applications, I mean, many limitations because the function that it learns is actually an approximate function, right? It's not it's not an exact function, and therefore at the edges it will give you wrong answers. So it can give wrong answers because again, it's what you learned is actually just an approximate function that maps features to label. And of course, you need lots of handcrafted data. Each narrow application needs to be specifically trained. But now, of course, you have large language models that, a little bit more general. And then, of course, the huge problems are explainability and interpretability because we have no idea. The model is a black box. The systems are opaque, essentially making it hard to gain insight. And that's where also we'll see, that logic actually can help and cannot do symbolic, it cannot do reasoning. It's pure pattern matching and computationally very expensive. We humans use only 12 watts of power, but these systems, you hear about their impact on global warming and all that stuff. So here are some examples of, problems with machine learning. So for example, researchers put stickers on the stop sign. You can see the picture here. And then these the self-driving cars actually did not recognize the stop sign. Of course, as a human, we have no trouble. Then the other one is where you can take some white noise and mix it up with a picture, and then the machine learning system will be actually the model, will get will be thrown off. So there's a picture of a panda, add some white noise, and it'll say, "Oh, this is a gibbon." Now you could say, well, I mean, in my case, I don't know exactly what a gibbon is. So, but here is actually more drastic. You have a picture of a school bus with some noise added, pixel noise added, and now the system says it's an ostrich. So there are these kind of challenges. And then, of course, there is this famous example with respect to explainability, where the system was asked to distinguish between a wolf and a husky. So a husky is kind of a dog. So wolf pictures of wolves had snow in the background, and basically the machine learning system just picked up that, if as long as recognize snow in the background, so it basically focused on that feature, and then it just predicts it's a wolf. So the model learned to associate a wolf with the presence of snow, and then of course it's predicting based on this presence of snow, in the picture, whether it's there or not. So obviously, if you have a picture of a husky with a snow in the background, now the system will say, "Oh, it's a wolf." So you see, and of course, we have no idea because it's a black box. And then, of course, autonomous vehicles or self-driving cars use machine learning technology extensively, and that technology, has. I mean, there are all these robo taxis and things, but robo taxis are really not fully self-driving in the sense that they get a lot of help. They were trained on the terrain, and they might even have sensors, and there might be people watching and all kinds of things. But fully self-driving cars that were promised have not materialized. So, for example, Elon Musk promised complete autonomy by 2018. In 2015, he promised this. He made this statement. And then in 2022, Tesla argued in court that this promise of full autonomy is a failure. They were accused of fraud. It's not fraud. So these autonomous vehicles can, only, so there's a scale of 0 to 1 to 5, or 0 to 5, I think 0 to 5, where they reach basically 3.5. So and even robo taxis, you cannot take them. Say, let's say they have been trained in Austin, Texas. You cannot pick them up and put them in, say, Dallas, where I am, because you'll have to retrain them. So again, essentially a universal function approximator. Then of course, we have generative AI systems and Chat GPT. I'm sure all of you have heard about Chat GPT, and it was released November 30, 2022. Of course, the large language model technology was being researched, since, since 2015 or even earlier. And by 2018, 2019, these systems already were there. But then they came into the foreground on November 30, 2022, when ChatGPT released its chatbot, and then it reached million users in 5 days. Still, you hear a lot about all this agentic AI and RAG and all that stuff. And it can generate these wonderful poems, article, essays, answer your questions, do all sorts of things. So, for example, I was giving some training to Marriott employees about AI, and then I asked it to generate a poem about wonderful hospitality at Marriott hotel chain, and it wrote a nice poem. And of course, you have these picture generation systems, so you can, DALI and many more, you know, um, uh, too many to count actually now. And so you can say, give me a painting of Egyptians arguing over whose turn it is to take out trash, and it actually generates a nice picture. So how do large language models work? So it's a different kind of AI, you could say. So you could think of it as example-driven search. So how does it do it? It works by essentially predicting. It tries to predict the next word, right? And again, I'm sure you already know, looked into how these things work. And the idea is that you essentially process, look at all the text that is out there on the web, and then you build these probability distribution tables that tell you, if I see these four words, then what will be the fifth word. And once you have done that, then remarkably, it starts, the more the more text you have, and you have to really get to, billions or trillions of sentences in order to get some semblance of correctness. There are weaker models as well that do not work as well. But once a lot more data was thrown in, it actually started producing text like a human. So for example, if I have the text, the best thing about AI is its ability to blank, then I might have a probability distribution table for this, which says learn occurs 4.5% of the time, 4.5%, predict occurs. And then you could pick the word that, is the most highest probability word that occurs after this. And in fact, these systems actually may not pick the most highest word with highest probability. They might pick the next one, and you can actually control that. And that's why it appears every time you ask a question or you ask it something, it gives a different response. Um, so Chat GPT again is a pattern matching device, and actually this is, you could say that LLMs, generative AI, actually show sort of a new way of um, achieving intelligent behavior, and that is by basically just focusing on examples. So for example, if you want to do planning, then instead of writing an algorithm, a planning algorithm like we traditionally would in AI, in traditional AI, what we can do is we can collect million or 10 million plans, successful plans, and then we build a probability distribution that says, in my plan, so planning is basically you're in an initial state, and the planning problem is that you're in an initial state and you want to achieve some goal state. And in every state, there are few possible moves that you can make. So it's like, trying to find your way around a maze. You can go straight, turn left, turn right? Depending on, the paths that are available. And your goal is to essentially go from the beginning of the maze to the end. So instead of trying to do some kind of search algorithm, you can actually do an example driven search. Take maybe 10 million traces of successfully finding, solving the maze problem. And then you look at, if you, in your initial situation, you find the most probable move by looking at your probability distribution. So there's absolutely no reasoning going on. It's pure pattern matching based on, essentially these examples. So you could play chess the same way, right? Take 10 million games, sequence of moves, and then you're playing by just sort of looking at these examples and saying what should be my next move. You have absolutely no understanding of chess, and the same thing is going on here. It has absolutely no understanding of the semantic concepts. It just understands, or really does not understand, just pattern matches the words. So here is an example. So I'll ask you this to solve this problem in your head. One car is traveling to Dallas at 40 miles per hour and travels a distance of 14 miles. Okay, so one car travels at 40 miles an hour and travels 14 miles. It's traveling to Dallas. Another car starts at the same point and travels the same route at 80 miles an hour. How far does the second car travel? So the second car is going from the same point, started from the same point that the first car started from, finished at the same point that the first car, finished at. So obviously they traveled the same distance. So the answer is 14 miles, right? That's what hopefully you calculated. So it's kind of a trick question. But Chat GPT, has to pattern match. So it's, oh, time equals distance over speed, and it took 35 minutes, 35, sorry, yeah, 0.35 hours. And now the second car is traveling at 80 miles per hour. So now, 80 times 0.35 is 28 miles. So basically, it's like, you really don't understand the problem domain, but you look at solutions to such problems, problems in that domain, and you see that you're always calculating the, time and distance and speed, calculating the third quantity given the other two, and you start doing that and you come up with the wrong answer. Okay, and then here is even more interesting one. So I asked Chat GPT. So again, I read this somewhere and I tested it out. It's so true. Draw me a picture of a clock with hands at 3 p.m. So basically the hand showing 3 p.m. Now all the pictures of the clocks and watches on the web show 10 past 10, right? So because, it uses pattern matching, it has no choice. I mean, the bias is so heavy that no matter what you ask, it'll always show you a clock showing 10 past 10, because every picture of a clock, as you know, always has, this configuration that you see here. So if everybody on the web said 2 plus 2 is 5, ChatGPT will have no choice but to say, hey, 2 plus 2 is 5. So you see the limitations. So even though you have all this agentic AI and all this stuff, fancy stuff, but at the end of the day, it is still pattern matching. So you cannot really trust the answer that you get. And I'm sure most of you who have used ChatGPT have encountered this situation where it actually gives you wrong answer. So I think any an answer of any depth, a factual answer of any depth will have mistakes. But of course, it's great for generating poems and all these things. So poems and letters, and it does a good job. So essentially, if you're regressing to the mean, I mean, if you what you're looking for, there is a lot of stuff on the web, then you will get a very good response. But anything else, or if you want factual correctness and your question is a little bit detailed, then it won't be as good. So can machine learning and large language models achieve artificial general intelligence? So that's the push. That's what all these companies keep saying. And as you might have heard, llama read llama's meta is not llama is the large language model is not performing very well, or the improvement they're trying to do. So they're trying to you know build better versions, and Meta was offering like $100 million packages to people with expertise to come and join their team. And there are all these reasoning large language models, but don't be fooled by the word reasoning, because they do not reason at all. It's all pattern matching, basically, still pattern matching. So reasoning, any reasoning that you see is what is embedded in the text that humans have performed and encoded in the text. So, can large language models achieve AGI, artificial general intelligence, or artificial super intelligence, as they say, which is essentially, the singularity, or whatever the name they want to give it, which is AI actually doing better than humans and taking over the world. And my arguments that is that machines cannot do better than, and I'll give the arguments, better than collective human intelligence. So can we trust LLMs? So that's the problem. So the answer is no. LLMs lack awareness. They don't know what they do know, what they know and don't know. I mean, basically, it's just again pattern matching. So there is no knowledge being extracted like we do. So machine learning essentially is sensing or pattern recognition, right? So essentially recognizing the pattern and then sort of predicting the next word. And I would argue that, in fact, this ability of sensing is there in not only humans but also in animals, for example. And actually, animals are much better at sensing than humans are. So dogs can, smell better, and eagles can see better, and generally animals are much better at anything related to sensing. But these animals lack advanced reasoning capabilities, and that's how humans can basically dominate. And so better reasoning capability translate to higher intelligence. So essentially the idea is that nature tried to make these pattern matching abilities better and better, but it did not lead to, you know, um, um, you could say, sort of smart intelligence as good as humans. So eventually you could say nature had to resort to reasoning, add reasoning capabilities, and only then, eventually, evolution, you could say, produced humans. Now, maybe, um, we're being too presumptive in saying that we are the most intelligent beings on the planet. Maybe we are not, but nevertheless, if you look at the evolutionary chain, then as reasoning capabilities improve, intelligent, you see, better more intelligent behavior. So there are two different ways in which brain processes thoughts, what's called system 1 and system 2. And this has been, very well, or this terminology um, was given in this book by Nobel laureate Daniel Kahneman, Thinking Fast and Slow, that again you may be familiar with. And basically, he said that human thinking is of two kinds. System 1 thinking is intuitive and fast. So, for example, if you look at a table, immediately you know that you're looking at a table, right? You don't have to think hard, or so all our sensory processing is all fast and is intuitive, basically. And then we also, act instinctively. So all that is system 1 thinking, basically recognizing pattern using our senses. And then system 2 thinking is slow and deliberative. And that's basically reasoning. So, for example, the sound of a siren. Now, nobody can actually describe the sound of a siren to you. You have to hear it. But once you hear it, next time you hear it, then you will use pattern matching to recognize it. But then in Texas, for example, where I live, if there are tornadoes, then sirens actually go off. So we get tornadoes, well, at least once a year. And then sirens go off. So once I hear the siren, then now I have to use my reasoning capabilities, at least the first time when I heard it, to find the safest spot in the house, so that there are maximum number of walls between me and the outside. And then you have to do reasoning. But then, of course, once I have figured it out, I can store that knowledge in my head and cache it. And next time I can just go straight to that room that is the safest in my house. So fast thinking is essentially based on sensory input and our instinct. Slow thinking is where, and so you could say that, all the machine learning systems are doing is essentially this fastest thinking. And really, we need slow thinking as well in order to achieve, human-like intelligent behavior. So another interesting point that I should make is, so there's recent research that shows that um, so the question is, can language processing alone produce intelligent behavior that is as intelligent as, humans? And is reasoning part of language processing? And the answer actually is no, according to neuroscientists. So this is a recent paper. Which year does it show? Oh, okay, actually 2024. Language does not appear to be a prerequisite for complex thought. It plausibly co-evolved with our thinking and reasoning capacity. So basically, area of the brain that processes language, which you could say is and does pattern matching, you could say, language related pattern matching, which is maybe, we have a process like chat GPT going on in our brain, because when we try to learn a language, reasoning does not help, in the sense that learning the grammar of a language does not help us. I mean, it's very hard. I cannot just learn the grammar of Spanish and say, oh, yeah, yeah, I know how to speak Spanish. I actually have to embed myself, and I have to build these probability distribution tables in my mind, so that, I can essentially, only then I'm able to learn to speak Spanish, or it's a lot easier that way than learning the grammar. So essentially, language processing and thinking are happen in two different parts of the brain. And another interesting thing that this is also recent research that so there's Pavlov's famous experiment which showed that animals learn by trial and error. Basically, the idea was that, I'm sure you're familiar, where dogs were given food. So first a bell was rung and then food showed up, and then eventually the dogs figured out that, bell ringing means that, the food is going to come, and then they would salivate, and then psychologists could actually measure that, and they could show. So the theory was that when a cue comes, like, bell ringing, then animals predict when a reward will occur, and then wait to see that it arrives. And basically, the theory was that it uses some kind of reinforcement learning, that you compute the difference or the error between the reward and the result, and then use it to make better prediction. But there are two problems that have always been there with this theory, namely the problem of time scale and computational tractability. And so the time scale problem is, how far in the future do you go to make this association, right? Is it, few minutes, one day, 1 year? And so that this theory cannot explain. And also computational tractability, in the sense that if you're looking into the future to correlate, then there are so many things to correlate. And how do you figure out which, what's the thing that you should correlate with? And so now recent research actually shows that there is more reasoning involved in this process than actually learning, or, reinforcement learning. So basically, what the brain is doing is that a reward event happens, then the animal actually looks backward. In this case, the dog looks backward for a cause, and then eventually finds that it's the bell ringing that explains it, or correlates to it, not explains it, correlates to it, and that's how it learns. So it's really not really, just correlating and learning. So many things that were attributed to learning are actually happening because of reasoning. And so recent experiments, and that's why it's actually, I think this is 2 years ago in paper published that in by neuroscientists that created a lot of upheaval in the neuroscience world. So if we want to build reliable AI systems or achieve AGI, then clearly things like um, ChatGPT, machine learning alone not going to help. And I would argue that, so for example, look at self-driving cars. So the promise was made 2018, we'll have self-driving cars, and here we are 6 years, 7 years later, and still, the promise has not been kept. And the same thing, and now we are seeing the same promises about large language models and generative AI. So again, super, interesting and very useful technology. And machine learning is an incredible technology, but that it will allow us to reach AGI or surpass humans is highly questionable. And machine learning is great because, again, you don't have to do any work. I mean, you collect data and then you give it to a machine learning system, and you're essentially sort of holding the data by its neck and saying, speak to me, give me your insight. And that's what a machine learning system is actually able to do. So how do we build systems that are as good as humans? So, well, we emulate humans. So we have the human, here we use we use pattern matching for, processing sensory input. So we see sight, sound, smell, touch, taste, and then even text input. And then we use all this to essentially um, uh, translate this into knowledge that sits in our mind. Right. So when we are driving, for example, right, we are processing, we are sensing, we see a human, we see the zebra crossing, we see the traffic lights, we see the road, we see the road markings. So we're building a mental picture in our mind, right? Then we check for consistency of what of the knowledge that we have accumulated, and also is it complete? If it's not complete, I will ask for more information. So for example, if you have to make a right, change lanes, your knowledge about that you're safe is not complete. So you look into your right mirror or left mirror, depending on where you're driving, here or in India. Well, anyway, you will look at your left or right mirror because you want to change lanes, and then that will complete your knowledge that it's safe to do so, right? And then you also check for consistency of what you're seeing. And then once you have consistent and possibly complete knowledge, you will draw a conclusion and take action. So we'll try to essentially combine learning and reasoning to achieve such, human-like intelligent behavior. So we'll use machine learning system for sight, sound, smell, whatever, text input, create knowledge, or, you know, uh, use the sensory input to acquire knowledge. I will represent this knowledge as logic predicates. And then we will check. So, of course, we have accumulated common sense knowledge. We'll use our accumulated common sense knowledge, right? That's what we do as humans. We have accumulated all this common sense knowledge that, for example, if I drop a mug, it will break and if it falls on the floor. However, if it's carpet, it won't, right? There's an exception to the rule. If I drop it on carpet, it won't because carpet is soft surface. So, and then once we have checked for the consistency and completeness of this knowledge using our common sense knowledge, then we can draw conclusions and take actions. So, current approach in AI is to tackle everything at system one. So, how do we build trustworthy AI systems? So, current approach is to tackle everything at the system one level. And, essentially, till large language models came along, then what people were doing, for example, you want to answer questions about a picture, then people will build these models where you take tens of thousands of pictures, and for each picture, you have 5 questions and 5 corresponding answers. And you throw this whole thing, these tens of thousands of pictures and associated question answer pairs into a machine learning system and hope that the model, given a new picture and a question, will be able to answer the question. But it was kind of, Well, I mean, it worked to a certain extent, but sometimes it would be hopelessly wrong. So for building trustworthy AI systems and achieving AGI, right, we should use, so a better approach would be to use machine learning, where I take a picture and learn the knowledge, right? Translate the knowledge of what is there in the picture, the components of the picture. Once I have this knowledge, then I can reason. So if you ask me, what is the object? Show me a picture and ask me, what is the object to the left of the chair? Then I have the representation of that picture in my mind. And then I'll say, oh, there is a chair. It's over there. Look to the left. So I'm actually doing reasoning. So essentially do the same thing. And then once we do reasoning, we can actually justify. So the road forward for AGI and building trustworthy AI system is to emulate humans, use machine learning, large language model, Gen AI for discovering knowledge, right? And extracting this knowledge as predicates and or ontology or whatever. And this discovered knowledge is our awareness. And then use automated common sense reasoning for processing this knowledge. So I may not be able to do a whole lot about. So processing means checking for consistency and completeness, using reasoning, and then drawing conclusions. So the consensus is that machine learning systems have hit their limit. And common sense reasoning is needed. But how to automate this common sense reasoning is basically the big research question. I only have so Bharat, how much time do I have? Is 15 minutes, right? I should try to wrap it up.
Yeah, that's good, Gopal.
Okay, so then let's talk about how to automate common sense reasoning, how to automate reasoning. So I probably will go a little bit faster. So that's where most of my research is. So why do computers have trouble in reasoning while humans can reason about things effortlessly, right? So our reasoning has, certain characteristics. So we actually work with incomplete information. And so we need, so traditional logic basically has failed in modeling, human thought or human reasoning. We have to use non-monotonic logics. So what we do is we revise earlier conclusions in light of new information. So we're basically able to work with incomplete information. If our information is incomplete, we still draw some conclusions. But as we discover more knowledge, we'll actually revise our conclusions. So given that the information is complete, what we're really doing is we are jumping to conclusions, right? So for example, I can't tell if it is cold outside. Then let's say it was winter and I wanted to know how cold it is outside. Then, I will look outside, or maybe it's, falls or spring, still mildly cold. I will look outside and see if anyone is wearing a jacket. If no one is wearing a jacket, I'll assume it's warm. But then, of course, there might be, people who are visiting from Canada or something for whom, let's say 5 degrees centigrade is really not that cold. So, right. So basically, I'm jumping to conclusions. But then if I discover, oh, these people are can tolerate much colder weather, I will, uh, you know, um, I will rethink. And then we also, as we reason, so we perform reasoning, but then we know that certain things are inconsistent. As we are reasoning, if we encounter this inconsistency, then we won't consider, those that line of reasoning. So, for example, we know that a person cannot sit and stand and sit and walk at the same time. And we'll actually use this knowledge to draw conclusions. So, for example, that if I say you know that I was in let's say in the laundry room and then I turned on a switch in the kitchen, you know that I must have walked. So let's say I was sitting in the living room and I turned on the light in the kitchen, then I know you know that I must have walked from the living room to the kitchen because otherwise I cannot do it because I know that person cannot sit and walk at the same time, and so I must have gotten up. So you see, you draw these conclusions. And then we can also deal with multiple possible worlds. So for example, um, if I ask you, do animals talk like humans? And of course you're going to say no, but then there is a world of cartoons where animals do talk like humans. So but in our mind we know that there are two possible worlds. There's the real world where Animals do not talk like humans, but there is the cartoon world where animals actually talk to each other. So we use non-monotonic reasoning and this non-well-founded reasoning in our day-to-day thinking that traditional logic has actually not captured. So we use this concept of negation as failure quite a bit. And so let me just quickly explain, what negation as failure is, and maybe then I'll skip the examples that I had so I can finish on time. So, so in our minds, we actually make a distinction between proving something to be false and and failing to prove that something is correct. So we make a distinction between what's called classical negation and negation as failure. So in our representation will represent classical negation as minus p, which basically says that p is definitely false. And think of this as, say, if I know that minus robbed Willie Sutton, who's a famous bank robber, minus robbed Willie Sutton bank one holds, which means I must have an explicit proof that Willie Sutton did not rob bank one. So only if I have an explicit proof that Willie Sutton was actually in Boston and the robbery happened in New York, I have an explicit proof, then I know that minus robbed Willie Sutton bank one is true. But in contrast it with this other notion where I try to prove that Willie Sutton robbed bank one and I fail to prove it, then I conclude that he did not rob it. So you see, so we'll denote this by not P. So I try to prove P. If I fail to prove P, I assume that not P is true. So, so if I want to show that Willie Sutton did not rob Bank One, I so ignore the not. I try to prove he robbed the bank, and I try to look for evidence. I fail to find any evidence. Then I say, oh yeah, he did not rob it. And in fact, in the courts, that's right. You need for at least for criminal conviction, you need evidence beyond reasonable doubt. You have to have a proof beyond any reasonable doubt. And if you have any doubt, then you say, oh, the person is not guilty, right? Whereas in this case, so you see the distinction between fail to prove something and then assuming that it is false versus explicitly proving that something is false. So we actually use negation as failure all the time. So we might say things like, and then the problem is that once we have negation as if we start, using this negation in our day-to-day reasoning, then, we can actually think very complex thoughts that we don't know what they mean. So here is an example that I give. So you have these four statements. Each statement by itself is actually easy to follow. Paul will go to Mexico if Sally will not go to Mexico, right? That's an easy statement to follow. But then I could have collection of such statements. Sally will go to Mexico if Rob will not go to Mexico, and Rob will go to Mexico if Paul, and so on. And now it's impossible to tell. So three people, and I have multiple restrictions. And so now I can actually turn it into logic and try to figure out so that several problems. What is the meaning of this negation? And how do we give meaning to such programs? So in order to perform reasoning, I have to basically be able to give reasoning. So I can translate this into prologue-like syntax. Say, Paul if not Sally, Sally if not Rob, Rob if not Paul, Rob if not Sally. What is the meaning of this program? Individual rules are easy to understand, but extremely. So there is this paradigm of answer set programming that actually captures this human thought process. And since I don't have time, I actually won't, spend too much time on it. I had a whole lot of examples, but I will just, skip over those, unfortunately. So let's just come to the actual applications.
So maybe you can come back another time, Gopal, and teach us about
Sure,
this.
sure. I'd be happy to.
Thank you.
So answer set programming actually models this sort of human thought process, you could say, or comes close to it. So it can actually model this deductive, and we also perform this abductive reasoning where, if we know that if it rains, the lawn will be wet. If we see a wet lawn, then we surmise that it must have rained. Of course, you might have sprinklers running too, right? So that's abductive reasoning. So answer set programming can express deductive, abductive, as well as inductive reasoning that is needed in machine learning for machine learning, where you're inducing, generalizing from examples. Okay, so there are many applications for which. So I built this. My group has built this implementation of answer set programming that actually emulates the human thought process, and we have built many applications where we can come very close to emulating human thinking. So, for example, we have built this system for treating congestive heart failure, where congestive heart failure is there are some 80 to 100 guidelines that cardiologists have to follow, and much of their training during their fellowship for congestive heart failure would be on learning these guidelines. And there are 80 to 100 of around, I think 80, 90 of them. I don't know, remember the exact number. It's a 100-page document. And these guidelines are basically saying, well, if you take this drug, I mean, for this particular thing, you must take this drug. But then if you take this drug, you cannot take that drug. Or these two drugs should be taken together, and they are the first line of defense. And then, of course, every drug may be contraindicated, meaning that person might be allergic to it. And then that contraindicated brings this negation into the picture. So we took these 80 odd rules and coded them in answer set program. And we actually were able to show, working with cardiologists, that the system can outperform cardiologists. And it's not that it's smarter than them. That's because cardiologists are humans. They will, for example, forget that the potassium value in the lab results change, where a machine would not, right? That's all. But they're basically emulating the same thought process that cardiologists have. I mean, use in their mind to treat. And in fact, there is a company in Finland that has actually used this system, our system, for building, used our, ASP, answer set programming system, for building systems for automatically treating diabetes. So basically, so chronic diseases are treated using guidelines. And so they actually have a system for, so there another one that they just got approval from European Union, and now the one for diabetes is in the process for getting approvals. We're also you can extract. So we also can use machine learning for extracting knowledge. So we've used this, for example, for extracting medical codes from electronic health records. So the idea is that you read the description that a doctor wrote, and in USA, the way reimbursement from insurance companies work is that doctors or hospitals have to submit exact codes that describe what was done, and then these codes are used to determine the amount of payment, the money that the doctors and hospitals will receive. But doctors write natural language text, and then there are medical coders who will read this text and create the code. And then they tried to use large language models for doing it, but it was miserable failure because only 60-70% accurate. And doctors are writing this informal prose. And so so we work with a company where we first extract the knowledge by the picture diagram that I showed, using machine learning or large language. So large language models are very good at translating text into knowledge expressed as predicates, because that's a pattern matching task. That's like translating English to Spanish, and they'll do a very good job because that's pattern matching task. And likewise, translate English into logic. That's also pattern matching. But once you get that logic, then I can perform reasoning just as a medical coder would. And then we can achieve nearly 100% accuracy. And then we also build reliable chatbots, and that's one example I will show, and then I will stop since I am running. And then, of course, you can also use such systems for automating, driving function, autonomous driving. So how do we drive as human drivers? We look at the scene, as I was telling you earlier, right? And then we process the scene and reason to figure out what my next action would be. So use machine learning, like these self-driving cars do, for understanding the scene, but then use reasoning for actually making the decision. Okay, so that's a press release for the. Okay, so let's just give me a practical example, and I'll stop. I have two more slides. So So basically, we use this technology to build chatbots that really understand. So in fact, the most recent chatbot that we have built is a chatbot that can actually handle, drive-through orders on a McDonald's or a Taco Bell. And in fact, McDonald's actually failed in building such a chatbot about 6 months ago. They were working with IBM because again, they're using primarily machine learning, and that has limitations. So it was suggesting, crazy things like, suggesting bacon bits as topping for ice cream and things like that. And we know that, that is not done. So, so the idea is that, you have a vocabulary that describes. So we're trying to build a chatbot that will act as a hotel concierge. You go to a hotel and you go to the concierge and say, can you recommend a local restaurant? So what is the knowledge involved in recommending a local restaurant? I must have, I should understand the concept of a restaurant, and I should have that restaurants have names. I should understand, what type of cuisine you want. I should understand the concept of a price range, whether you want a family-friendly restaurant or a bar. And you might have some preferences, like, you want to eat, say, noodles, then I'll recommend a Thai or a Chinese restaurant, right? So then I have common sense knowledge, right? That, if you prefer to eat curry, or then I would recommend a Thai or an Indian restaurant, right? So we trained an LLM to extract, given a sentence, extract the predicate. So I'm looking for a restaurant that serves curry, for example. Then we'll generate, you're actually looking for a restaurant name. So LLM will generate this through, and it's very simple training. You just give some examples. So that way LLMs are great. I mean, so for example, if if I tell this system, if it asks me what's your budget, and I say I'm a student, it actually correctly infers that my budget is, it translates it to the predicate that my I don't want to spend too much money. So here then it generates that you're looking for a restaurant. Query is a keyword suggesting that you actually want to know the name of a restaurant, and then your preference is curry, and then we code the knowledge in our system as CASP. And then, of course, you can justify why for every recommendation that you made. And so you have this part that extracts the predicates and then the part that processes it. So here's an example conversation. Hi there, how can I assist you? And the user says, can you recommend me a restaurant? And these are the predicates that are extracted by the large language model. So think of large language model as being used as a semantic parser. And this was the biggest challenge in building chatbots, right? What does the sentence mean? We have no idea. So, and all these machine learning based systems, purely machine learning based systems, were just doing some kind of pattern matching and getting it horribly wrong, right? Anytime you go to a website and use a chatbot, in 2 rounds of conversation, you just quit, because they're hopeless. Now, you could use large language models, and they're doing that for building today's chatbots, but they cannot still, when it comes to accuracy, at some point, some rounds of conversation, it will, give wrong information, almost guaranteed. Is so the Then the bot knows that its information is incomplete. So, is there a particular type of food you would like to eat? And you say, I can try any food except curry. Now it knows, your common sense
Yeah,
knowledge
can do.
knows that you must not recommend
Tell me.
Indian or Thai food. Right? So
Hmm?
this is a knowledge
Yeah, I'm
extracted.
still in office.
And then the bot will keep going and trying to complete its knowledge. So it basically has this idea in its common sense knowledge. It has an idea about um, what to ask, what it needs to know. And so it will basically keep asking, and then eventually, once it has figured out all the information that it needs, it will give you a recommendation. Use the engine to give a recommend the reasoning engine to give a recommendation. Now notice that when we give information, humans give variable amount of information. So I might say I'm looking for a Chinese restaurant, or I might say I'm looking for a cheap Chinese restaurant that is family friendly, or I might say I'm looking for a cheap Chinese restaurant for my son's birthday party. And son's birthday party automatically implies that you're looking for a family friendly restaurant. So you have to be able to take care of all this. And that's where this approach, where we extract the predicates, and based on the knowledge that I have, I will draw my conclusions. And at any point, I can say, I could have said in the first step, I don't care, just tell me a restaurant. And then, the reasoning engine should be able to answer, without having any information. Just then you randomly recommend a restaurant from your knowledge base. Okay. All right. So that's it. Sorry. I should skip this. Okay. So conclusions. So machine learning and generative AI are impressive technologies, but they're pure pattern matching devices with no correctness guarantees. And we want to address the problem of developing trustworthy or reliable AI systems. So we essentially argued that reasoning is indispensable. And so one thing I should mention is that reasoning has its limitations. So as you know, as computer science students, that automated reasoning is undecidable, and it suffers from the problems of incompleteness, in the style of Gödel, where there will be true statements that you cannot prove to be true. And of course, it's knowledge. I mean, reasoning is also our reasoning is non-monotonic. So because of these problems, we cannot automate reasoning and expect to do better than humans. So essentially, artificial superintelligence is not achievable. Artificial general intelligence we can achieve, but the best we can do is be as good as humans. So for building reliable AI systems or AGI systems, we use machine learning. We should use machine learning to convert sensory input to knowledge and use reasoning in the back end. And then, of course, I described applications. Okay, so I will stop here. And if you have questions, sorry for going a little bit over time.
Uh,
Thank you.
thank you so much, Gopal. Uh, very, very stimulating lecture. Clearly, there is a lot more that underlies this technology that we should learn about. Uh, if there are one or two questions, we can take it. I wanted to say, for the benefit of everyone, that AIAR will have a YouTube channel, and we will post the video over there, subject to Gopal's approval,
Sure, sure. I'm happy. Yes, yeah, absolutely.
and so that we reach the maximum capacity of 100, Gopal, and so some
Oh,
people
wow.
could not get in to your lecture, and there have been several messages and so forth that I've been seeing, asking for it to be posted, and we'll do that. So I'll just open it out to questions now, and maybe you could stop the screen sharing, and we can see maybe
Okay, sure.
the audience here. Those who would like to turn on their video, are most welcome
Okay.
to do so,
Yes.
so we can see them. Yes. Um, yes, Mailesh, please.
Okay, so Dr. Gupta, wonderful presentation. I would like you to elaborate very briefly. What do you mean by abductive reasoning?
Okay. So yeah. So abductive. So very good question. So um, abductive reasoning. So basically, our generally we're familiar with deductive reasoning, right?
And
So
inductive, right?
so if we say, so if I, for example, know P implies Q, if P then Q, right? So I have this statement, and then I know that the antecedent P is true, then I can conclude Q, right? Which is modus
Mhm,
ponens. So
mhm.
abductive reasoning is sort of reverse of modus ponens. So I know that statement if P then Q holds, and I observe Q, then I surmise that P must be true.
Okay.
So it's not sound always. So for example, if I know if it rains, then the lawn will be wet, and I observe. So obviously deductive reasoning will be it rained, then I know
Mhm.
that the lawn will be wet for sure. But then I know that if it rains, the lawn will be wet, and I observe that the lawn is wet. Now we will work backwards. So that's abduction. We work backwards to conclude, to hypothesize that it must have rained, or maybe the sprinklers turned on, or whatever. So basically, abductive reasoning, we use it quite a bit in our everyday life, because we're working backwards to, oh, this must have happened, and this must have happened, and a lot of um, um, detective sleuthing is done through abductive reasoning, right? You try to explain. And so abductive reasoning is an important part of common sense reasoning or human thought process, human thinking. And that we should be able to, automate as well.
But
So
how do you rule out the expanded scope of fallacies getting introduced?
So the fallacies, I mean, in the sense that if your system is sound, if your knowledge is sound, then you can get rid of fallacies. And a lot of I mean, you will not have fallacies. Now, a lot of these fallacies actually come about because of trying to avoid cyclical reasoning. But actually humans do cyclical reasoning as well, which cyclical reasoning is essentially an assumption based reasoning, right? If we assume that it rained, then the lawn will be wet. So so fallacies in general will not arise. But as I was saying, maybe we need to have offline discussion. So
Okay.
we need to revisit this whole idea of logical fallacies, because a
Yeah,
lot
sure.
of these logical fallacies, and the history goes back where, in 100 years ago, Russell said only well-founded sets, only well-founded reasoning. And so fallacies arise because of non-well-founded reasoning. But we humans actually do non-well-founded reasoning as well. So it's, hard to
Yeah,
explain, but yes, yeah,
yeah,
Yes, another
yeah. Thank
reason
you.
that we should bring back Gopal another
sure,
time,
sure.
to explain the subtleties. Abductive reasoning is a full topic unto itself, and Gopal has done a lot of work in that area. Um, any other comments, questions? Gopal, just in the interest of time, so if you don't mind, we will close the lecture at
Sure,
this point.
absolutely.
Huge thanks to you for
Oh, no,
taking
no
the time
problem.
and for
My
sharing
pleasure.
your insight on this very important topic. And thanks to all the attendees.
Yes,
I know
thank you.
many from India. It's Friday evening, and you've still
Right,
made the
right.
time to be here, and it's greatly appreciated. We'll post the lecture on YouTube, and I will keep you informed about the subsequent lecture in the lecture series. Thank you very much.
Absolutely. And I should mention that there is a lot more information on my homepage. So if you just Google my name, you will see my homepage, and there's lots of papers and lots of things that hopefully you'll find useful.
Thank you.